First, let us see what is shear practically. See, this is a simply supported beam. Uniformly distributed load is acting, right? I am not showing here the bending moment diagram and shear force diagram. You remember the load is uniformly distributed load, so bending moment diagram will be parabolic. Maximum bending moment will be at midspan. And shear force diagram will be straight line, maximum near the support and zero at midspan. So this is a beautiful thing. The location where bending moment is maximum, shear force is zero. Where bending moment is shear force is zero, bending moment is maximum. Two contradictory things. But we have to design both for bending moment and shear force, right? Now for bending moment, we had already designed either by single reinforced section or by double reinforced section. Now we have to do shear force that I had discussed in our last class. Now, physically you will be able to see it. Now say at the location 2, that is at midspan point, shear force is 0. Shear force is 0. So since shear force is 0, we are not in complicacy with respect to shear. There is no situation for failure of shear, so we do not require any design with respect to shear. Now as we move from the point 2, that means from midspan point towards the support, our shear force goes on increasing, and it is observed that shear force is maximum at support. Now next, you have studied this bending stress distribution and shear stress distribution. On the cross section, bending moment is at location and shear force on the section. Do you see my hand, left hand? Anyone? Do you see my left hand?
Yes, sir.
Do you see my finger of right hand?
Yes, sir.
It's very good. Now this finger of my right hand is whatever beam is shown on the laptop. On left hand, on this side there is an arrow, so there is support. On this there is an arrow on support. Now you try to see the movement of my left finger. For this beam, support is here. Our bending moment diagram starts from 0. It goes this way and this way and this. So here it is maximum. And shear force, here it is upward, here it is downward, and this peak point and this peak point is to be connected. Okay? Okay. So it is observed that at point 2, bending moment is maximum, shear force is 0. At point 3, shear force is maximum, bending moment is 0. So from bending moment point of view, we do not require any reinforcement here. For shear point of view, we do not require any reinforcement here. So in between, as we move from midspan to support, we can reduce the reinforcement required with respect to bending moment. But contradictory to, we have to increase the reinforcement for shear as we move from 2 to 3. Now why? So these diagrams are from your strength of materials. This is element 1, that means at this location. First, let us discuss here. That means figure 2, this figure. So in this figure, the member is subjected to only bending moment. At this location, the member is subjected to only bending moment, no shear force. So at that section, if I cut here, the section, again, you see my left hand. You see my left hand, this is the plan. So here, only the axial stress on the bottom, tension, and at top, compression is acting. This is axial on the section. So this is with respect to bending, right? Now here there is shear force. So if there is shear force, together with this axial along this surface, hmm, tangential stress. This is also called tangential stress. Hmm. So this is acting. So both shear as well as axial is acting. Now this is the location. This is the location point 2, section 2. Only axial stress is acting sigma maximum. No shear stress. But here, that means at this location. So here, element here at this location, both bending moment and shear force is there. So both axial stress and shear stress are acting. Shear stress acting. Shear stress are always at a complementary. Actual shear stress is acting this and this from our bending moment diagram. From bending moment diagram, these two are acting. But for balancing this, we have to apply this and this. This is the complementary. So this is the situation where sigma is the bending stress, tau is the shear stress. Okay. Now come to this situation. This situation. So in this situation, what is happening? There is no bending moment, only the shear. So this is this. Somehow here should have been also one arrow on towards right that is missing somehow. When I have made some scan, it is missing. So similar diagrams are here. Now see here, physical representation is given here. Because of these two, see the axial is not there. Axial is not there. So only these two sets are acting. Tau maximum, tau maximum, tau maximum, tau maximum. Now this tau maximum and this tau maximum, it is producing a couple. It is producing a couple, and here is a tau maximum, and here is one tau maximum. This is another couple. So because of this, again, are you looking my hand? Are you looking my hand? Because of
Yes, sir.
there's a tendency to come this way. It is a tendency to come this way. So here, in this element, there are two diagonals. This is one diagonal, and this is another diagonal. Because of these two sets of forces, this here was there, somehow it is, at the time of scanning it is missed. This two has a tendency, this diagonal has a tendency of elongation, and this diagonal has a tendency of contraction. Now see here this figure. So this has a tendency of extension, and this has a tendency of contraction. And because of this, along this axis, it has a tendency of tension failure. It has a tendency of tension failure. So that is the magnitude. That is the magnitude we have to find out. You have to find out, and for that, since along this line there is a possibility of tension, so this tension failure is to be resisted. Okay, so how we will resist? How we will resist? So that we will be able to resist with the help of using shear reinforcement. So what type of shear reinforcements we are going to provide? Now let us see. This. Design of shear reinforcement. So this is as per clause 40.4 IS 456. So this is the vertical stirrup. These are the vertical stirrups. Now see here, these are the dots, dark dots in all the figures. In all the figures, these are the main reinforcement of the beam. It means these dots, say with respect to these dots are these. Oh, these are the dots. These are the dots. Okay, that means those are the dots. If we provide, see the movement of the arrow. So if we are to provide reinforcement here, we are to provide reinforcement here. Okay, so those dots. Okay, so those dots are to be encoded. This is the stirrups. These are called stirrups. These links are called stirrup. Right? So this is, if it is single, it is a simply supported beam. This reinforcement, these reinforcements are for if single reinforced for tension. So this is tension reinforcement, but always we have to provide some reinforcement in compression zone. If at all we do not require. So if we provide, if we do not require, those reinforcements are called hanger reinforcement or reinforcement required with respect to construction point of view. Now see, this is linked. See, this is a single leg. This particle part is called leg. Okay, here is only one vertical is there, but here two verticals are there. So that's why it is two legs. And here four verticals are there. 1, 2, 3, 4. Four verticals are there. And here 6. 1, 2, 3, 4, 5, and 6 legs. Depending on the situation, we may require any one of these. But single leg stirrups are rarely utilized. Normally, in all the cases, it is two-legged stirrup. Sometimes we may have to go. Now, see what is the purpose for stirrups? How we will use it? See. Now, diameter. See, these for this main reinforcement, we had already got our idea what should be the diameter of the main reinforcement. Normally, it varies from 12 to 25 in normal construction. If it is an unusual structure, heavily loaded structure, then we may have to go for up to 20 mm diameter. In normal construction, it goes from 12 millimeter diameter to 25 millimeter. Now these are the stirrups. These are the close leading you are to make this. Now this diameter of this varied theoretically from 5 millimeter to 16 millimeter. But very rarely it is 16 millimeter. Again, with respect to heavy construction, heavy structure, like 60 millimeter. Because normally, in our normal construction for RCC residential building, even it is a 10 story, 12 story, normally it varies from 6 millimeter to 12 millimeter. But again, 12 millimeter is rare. 6 millimeter diameter to 10 millimeter. It is universally accepted. Okay. They see the free ends of these things we will discuss later very clearly, depending upon this. Okay. So this is the vertical steps. Sometimes, see, this is a cross section. So this is our compression reinforcement or hanger reinforcement. And the bottom one, is the main reinforcement. 1 minute. So, Sorry. So see these are the rods. See, this is a section. This is coming from this way. Now this reinforcement at bottom. No, I already told that the bottom reinforcement, since bending moment near the support is zero, or bending moment from midspan to the support gradually reduces. So whatever reinforcement with respect to bending moment is provided for the maximum bending moment, that is at midspan point, need not require throughout the night. Out of this reinforcement, we can curtail, we can reduce at some distance from the support, or we can say from the midspan point. Now, if this reinforcement we can utilize, not cutting, not curtailing, for some other purpose, then it will be economical. Okay, so if this reinforcement is bent up, see our see here I had told you that the shear failure is going to occur. Shear failure is going to occur. Shear failure is going to occur with respect to this figure. With respect to this figure, shear failure is going to occur along this axis. Along this axis, it has a tendency to see here diagonal crack. Along this part has a tendency to go on this side, and this part has a tendency to go this side. So here, if we provide some rod in this way, see the force is acting this way, force is acting this way. This is to be resisted, so a particle component of this force will be resisted by this, and particle component here will be resisted by this. Okay, with stirrups. Now, if we provide axial force is acting in this direction, axial force is acting this way. If we provide a rod this way, so this will be able to resist the axial force. Okay, so that we can do. So that we can do by making this bottom rod, you raise here to top at some distance, and then again you bend it this way. So the same rod is giving resistance to shear, and same rod is giving hanger at top also. Okay. Now, what is the magnitude of shear force for this? Now, this expression, 0.87 Fy ASB d by SP, you need not remember. You will get it in IS 426. Okay, very simple, right? So, differently, we can resist the shear only by vertical stirrup. Vertical stirrup means the alignment of the stirrup is perpendicular to the longitudinal axis along y direction, and it is to be given at some spacing throughout the length. At some spacing throughout the length here, SV. In both the expression, the SP is there. SP is the spacing of stirrups. Okay, this is available in your IS 456. You need not worry. Okay, then we can do this. Either this or this. Either stirrup or by bent of bar. Now, question is coming. By bent of bar, we cannot raise up. We cannot raise up all the bars required for bending. Only some bars will be able to raise up. So that we will talk in our next one chapter. At least 1/3 of the main reinforcement, whatever required at the bottom, as tensile strength, should extend to the support. if it is simply supported beam. For continuous beam or frame, it will be something different. If it is a simply supported beam, at least 1/3 of the reinforcement should go to this support. So rest will be there. So with this expression, we'll be able to find out this value. This value. Now question is here this value. Huh? We'll be able to find out this. We know this shear force. Definitely, whatever value we'll be able to obtain with respect to this will not be equal to whatever shear force we have obtained. Whatever shear force we have obtained. So full shear force will not be possible to resist by pent-up part, since there is a restriction that all amount of reinforcement cannot be bent. So balance part will be able to resist by the vertical stirrup. IS code again restrict the shear that is to be resisted by the inclined stirrup or bent up stirrup. Bent up stirrup cannot be more than 50% of the shear to be resisted by the shear reinforcement. What is shear reinforcement? That's now what we have. The third category is inclined stirrup. Inclined stirrup. See here, these are inclined stirrup. So here, see here, these are vertical stirrups. The vertical lines, these are vertical stirrups. This is inclined bar, not stirrup. The bottom bar is raised. The bottom bar is raised to top, then it's bent. So it is combination of combined vertical stirrups and inclined bar or raised up bar. But what we can do, we will not bend up any bar from bottom to top. Since shear is acting along the diagonal, so shear reinforcement will also provide along the diagonal. Again, if we go to the first figure, no, here. So the member has a tendency to shear off along in this plane. This part has a tendency to go this side, and this part has a tendency to go this side. So if we provide reinforcement along this diagonal, then it will be okay. So if we want to provide reinforcement along this diagonal, then, and if this reinforcement are stirrup, so it will be inclined stirrup. It will be inclined structure. But use of inclined stirrup is not easier. Not easier. So why not easier? Because it is inclined. To keep in position, it is not easier. Okay. So there are three types of arrangement to resist the shear. Now, out of these three, commonly utilized shear resisting system is stirrup. In our normal construction, say for a building construction, the bent up bar system is normally avoided. It is not prohibited, it is avoided. Because consumption will also be time consumption will also be more. So under that situation, what is done? Not bending up the reinforcement. Normally, it is curtailed. It is curtailed. So here, one bar is raised up. So in our present situation, this bar is not raised up but curtailed here. Okay. Then come, why we wear stirrups? So before that, why we require stirrup is a question. Before that, we have to raise a question. Whether the concrete is having its self-capability to resist the shear. That first question will place. Then whatever main reinforcement we have provided, whatever main reinforcement we have provided as tension reinforcement or some amount of reinforcement we are keeping near the support, whether those reinforcements are giving any influence for resisting the shear. Okay. Now this main reinforcement, whatever available near the support, will give influence, some influence on the resisting the shear. Will give the resisting the shear. So that will get just now. Okay. Now concrete is also giving this. Now from construction point of view, sometimes the situation may come that the beam is of such type of size that whatever shear force is acting on the member, it is able to resist the concrete together with the main steel. So under that situation, you do not require any shear reinforcement. You do not require any shear reinforcement. That's theoretically that situation may arise. But although theoretically we do not require any shear reinforcement, but from construction point of view, we have to provide the shear reinforcement. Why? Number one, so this is the beam. This is the depth of the beam. This is the depth of the beam. This is the depth of the beam. Now go to, let us count, say, this is the cross section of the beam. This is the cross section of the beam. This is the cross section of the beam. Okay, now again, let us count one figure, whatever we had drawn at the very beginning. This is the cross section. This is the cross section, right? So here I had shown reinforcement at bottom, no reinforcement at top. It will be not easier to keep the concrete in this way. In this way. Okay. So to keep this section, although we do not require any reinforcement here, we will provide reinforcement here. That means in a concrete member, at near each corner inside this section, you have to provide at least one number of bar. One number of bar each corner. So here also we have to provide. Okay, we have to provide this. Now come to this figure. Come to this figure. Come to this figure. So those rods are these. These are the dots along the lengthwise direction. Okay. Now during the concrete, this reinforcement, whether we will be able to keep in its position, yes or no. We will not be able to keep in position. It will move. It will move. So to keep in position, we have to bind all the rods, both at bottom surface as well as top surface. So for that also, we will require the stirrups. Number one, to keep the main reinforcement in its specified position, we require stirrups. Number one. Second, concrete, it is normally it bulges out. It bulges out. So if there is no any vertical reinforcement, vertical preventive system, the concrete along the breadwise direction, there is a possibility of bulging out. So to prevent the bulging out, we require some type of reinforcement. So that bulging out will be able to resist by the stirrup. So that's why we require minimum stirrups. Number three, the rods. There is a possibility of compression. The upper rod will be subject to compression. See, the diameter of the rod is very small. So the compressive stress is acting along the longitudinal axis of the compressive rod. So it is a compression member. It is a compression member. So the compression member will normally compressive stress, that is permissible compressive stress or maximum compressive stress, is again dependent on slenderness ratio. Look at slenderness ratio is L by R. L by R, slenderness ratio. R is least radius of gyration. I is equal to AR square. Now, L by R. R for a particular diameter of rod remains constant. So if L increases, our L by R ratio increases. So it goes on gradually. Slender and slender. So its axial load carrying capacity will reduces. So that's why the particularly for the reinforcement in compression zone should be find out so that difference between 2 points goes on reducing. So say if that means we can call say from this point to this point it is the length. It is the length. So this is the length. This is the L. We know the cross-sectional diameter of this, so we can find out R. So L by R will get value. If suppose this we remove, so in that case L will be this. So L will be this. So L increases. So L by R increases. So slenderness increases. So load resisting capacity of the same rod. Load resisting capacity of the same rod will reduce. Will reduce. So that's why also we require the stirrup. So you got number one, use of stirrup. Number one is to keep the reinforcement both in compression zone as well as tension zone in its own position to prevent the bulging out of the concrete. To increase the axial load resisting capacity of main rod in compression. In tension zone, no problem because it is in tension, it is in material, whatever is the length. Okay, so these things you have to got it. Now, then what is the thing and how to design it? How to design it? See here, these things I have told. Design of staying. No, these things I had not told, but some information I will design of shear strength. So design of shear strength is shear force we got. So nominal shear stress we will be able to find out. Nominal shear stress is equal to maximum shear stress, shear force divided by effective section. Effective section. Okay. So for that the expression is at the very beginning. Tau FR is equal to this, then tau V. Tau V is the nominal shear stress, VU is the vector shear force, and B is the width, and D is the effective depth. This is the nominal shear stress, tau C. That is induced shear stress, right? Now, nominal shear stress for members with varying the resolution. Now, we have to find out whether whatever shear force, shear stress, shear force we had calculated from theory of structure. Then shear stress we had calculated from the strength of materials. Now, this shear strength, tau C, should be able to resist by the cross section of the member concrete together with steel. Concrete together with should be able to resist it. If it cannot resist, then we'll have to think other things. Then how? Now see here. The tau C. How will be able to this tau V? This tau V. Then we will to find out what is the load resisting capacity of the section. See, load resisting capacity of the section and load induced. Shear stress induced and shear stress capability. Shear stress induced, we can find, we are calculating from the shear force that we had obtained from pure pressure. Then shear stress induced, we'll be able to find out from the cross section together with the amount of steel. Now, where the support from the design of with respect to bending moment, we know the amount of steel. Say that is A capital ST. Okay. We know the effective section, we can find out the percentage of steel that is provided. So percentage of steel is equal to area of steel available at the location of shear force divided by effective section, DD. PT, this is the PT. Now, in IS 456, there is a table. This is the table. Table 19, shear strength, tau C. So the first column represents 100 AST by PD. That means percentage of steel. Percentage of steel that is provided near the support. Okay. Then we utilize the concrete type of concrete. Say it is M20 concrete. Say percentage of steel is 0.2%. So now come here. Say 0.2%. It is not here. 0.15, 0.25. So it is somewhere by interpolating we can find out. So if we talk say 0.25%, so 0.25%, it is M20, that is 0.36. That means 0.36 Newton is the capability to resist the shear by this particular section. 0.36 Newton per millimeter square is the resisting capacity of the section. Now, that means we know this tau V and tau C. Shear stress induced, shear stress capability. Now what is happening? If tau V is less than tau C, that means induced shear stress is less than capability of the shear stress. Whether the section is in danger or is in suffer. Anyone? Shear stress induced is less than shear capacity of the section. Say, you can call it this way. You are going to the market, you are paying 100 rupees. So you are having the capability to purchase for rupees 100. Okay, you cannot purchase more than 100 rupees, more than you can, you have got that thing is 90 rupees. Now whether you be able to purchase it or not. Do you hear me? Whether you will be able to purchase, you are having 100 rupees in your pocket. The cost of the material, whatever you want to purchase, is 90 rupees. Whether you will be able to purchase it or not. Yes or no?
Yes, sir.
Okay. Yes. Very similar things. Same things. Tau C, tau V. Tau V is the price of the material, whatever you choose. And tau C, the money in your pocket. You have that capability, so you can purchase. You need not borrow from somebody. So here also, if tau P happens to be less than tau C, we do not require any shear reinforcement. It will survive. So under that situation, we will be required to provide nominal shear stress. So for that, some expression is there. Okay. So how to find out tau C? This table, IS code will be available in your hand. It will be permitted in your zone. From here, we will be able to find out the tau C. So if tau C is greater than tau phi, no shear reinforcement required. But if tau C happens to be less than tau phi, same thing, you are having your rupees 100, the material, whatever you want to price, its cost is 110 rupees. Now, whether you will be able to purchase it or not. You are paying 100 rupees in your pocket or money bag. The price of the material is 100 to 110 rupees, whether you will be able to purchase it or not. You will not be able to purchase, you will be required to borrow 10 rupees from somebody. So here also think. So the difference between tau P and tau C is the stress for which we require shear reinforcement. For which we require shear reinforcement. Okay, this part I will talk later. Now, sometimes, or it is not given that infinite value. There is a maximum limit which is called tau C maximum. Now see here again, it is in the code. Maximum shear stress tau C maximum. Tau C maximum. There is a table number 20. Table number 20. This is the table number 20. As per IS 456, say with respect to grade of concrete, maximum value is given. That means your induced stress cannot be more than this. Okay, for M15 it is 25, and this it cannot be more than this. It may be less than this. It cannot be more than this. If it is more than this, then under that situation, what will be required? Either you will have to redesign this section. That means either you have to increase the breadth or depth, breadth and both depth, number one. Number two, or you can increase the amount of main step. Any one of these two. Okay, by this way, we'll be able to find out, we'll be able to reduce the value of tau B. We'll be able to reduce the value of tau B. Tau B cannot be more than tau C maximum. So under that situation. Okay. So this is the, I told that minimum shear stress. Again, it is with respect to clause. So this is the expression. This is the expression ASB by BSB greater than equal to 0.4, 0.87 FY. Again, this is in your code. Okay. So from this, we will be able to find out. We'll be able to find out again this. Our basic interest is SP. ASB. ASB is the area of stirrup. Area of stirrup. So we'll be able to find out spacing. Okay. So design of shear reinforcement, this is things I had got. Now, let us take a simple problem, something I had not told you up till now. See, a rectangular beam of effective section 225 by 450 is reinforced with 3 numbers 20 tall. Try to remember this. Represents 23 numbers 20 tall. Determine the maximum shear force that can be resisted by the beam. Whatever I told, I just want to show this example. So we got AST is equal to, see, the diameter of 20, say cross-sectional area is 314 millimeters. So this. So PT is equal to AST by BD into 100, so 0.9. 0.9. Then with respect to again this table M20 concrete, PT is equal to interpolation we get 0.596. Okay, and from table is point the 2.8. Now induced shear stress induced in this capacity is 0.596. So under this situation, This we need not write. Maximum, this maximum we do not write because we are not we are not having to calculate the induced shear stress. So this much of shear capacity 0.596. So maximum shear force will be equal to shear capacity multiplied by affected area. So 63.345. 63.345. This is the shear capacity. Okay. If the shear force induced, PUC means shear, probably somewhere PUC means shear, ultimate shear resisted by the section, or we can say ultimate shear resisted by the concrete and main steel. Concrete and main steel. Very simple. Very simple. Now suppose here in this same problem, I want to introduce some stirrups. Okay. Now see here. Same problem. Only thing that 8 Tor bar 2-leg stirrups are used as at a spacing of 140 center to center determine the maximum shear force. Now see 8-5 2-leg, that means this figure, this is 2-legged. 3 numbers of 20, that means this is 1, and here will be 1. Okay, then this is SP spacing. So these are 8 diameter rod, and this is the spacing. This is the spacing. Okay, that means this figure will be useful minus this inclined part. Okay, now with respect to this, we had already calculated the shear that can be resisted. Now see here, the first part up to here, up to here remains constant. Up to here remains constant. So here I have written clearly maximum shear force resisted by the section together with main steel. Main steel means 3 numbers of 20 torque. Now we have to find out the shear that can be resisted by the stirrup. And maximum shear that can be resisted by the stirrups, PUS is equal to 0.87 FYASP SV times that expression. Whatever expression we have here, you see, here you see 0.87, Fy is 415, 2 is the number of leg, ASB is equal to small ASB times n times small ASB. That expression I had get there. 2 number of leg is 2 and 8 mm diameter. For 8 mm diameter, our cross sectional area is 50 millimeter square. 50 millimeter square. 50 millimeter square. So from that we will get the total shear force that can be resisted by the member is 176.397 kilonewton. Okay.